Welcome back to Business Analytics. This is your professor, Hari Rajagopalan, and I will be taking you through continuous distributions this lecture. So remember when we looked at the analytics aspect and we talked about the different modules, descriptive, predictive, prescriptive, risk analytics, and then decision-making tools. We're still at descriptive analytics right at the start. And we are looking at data distributions, and we went through a bunch of discrete distributions, and now we're going to focus on continuous distributions. And we are going to look at uniform, exponential, normal, and we are also going to talk a little bit about triangular and log normal. So let's look at some continuous distributions, and we'll start with exponential distribution. We're starting with exponential distribution because we just finished our discrete distribution using Poisson distributions. So exponential distribution is an inverse of Poisson distribution. And in this case, remember in Poisson, we were talking about average number of events per unit time. Now we flip this and we look at the average time between events and we try to figure out the probability of that event happening. Let's take an example. So remember this example where we looked at, it takes about 50 minutes or 50 hours or 50 days before the first failure occurs. Then was 75 days before the second failure occurs, right? But now if we were looking at the time to failure, so it was 50 days for the first failure, then 25 days for the second failure, then 50 days for the third failure, and then here another 75 days for the fourth failure. You can find the average time per failure, and that's what we have here. You can look at waiting time, average time for the bus to arrive, and as I talked about before, this is the inverse of Poisson distribution. Now notice that Poisson was the probability of getting so many events in some period of time, right? That's what we talked about. And this is the probability of average time, the probability of getting the next event in the block of time. So here's how exponential looks like. This is called a negative exponential. And the average here, lambda, is for 0.5, it's this red line. For 1, it's the black line. And as you see, as the average time increases, the line gets steeper. So let's compare Poisson distribution with exponential distribution. So if you look at Poisson distribution, we are given this input. The average here is given as 2 customers per minute. Let's say we are looking at arrival rate, right? 2 customers per minute are coming into your shop on average, right? So sometimes you could have 4, sometimes you could have 0, but when you average them out, you end up with 2. Now the same average 2 customers per minute under exponential distribution will actually come out to be 0.5, which is essentially 1 divided by 2. It's every half a minute you're getting a customer on average. So see the difference between this and this. So the questions you ask with Poisson distribution is, what's the probability that you're going to get 0 customers in the next 1 minute? So you're going to use Poisson distribution, 0 customers, select that. You can select the average here, that's F4, make sure it doesn't change, and put cumulative as false because we're looking at what's the probability you are going to get exactly 0 customers, right? So that comes to 13.53% chance that in the next minute you don't have any customers. And now you can, because you put this $sign for B3, you can copy this down up to 20. So here's what we've got. You have a 13.53% chance you get no customers the next minute. You get a 27% chance that you have 1 customer. You have a 27.0 that you have 2 customers, right? So now let's look at copy this same formula here. We are going to change this to A5. So here the same question you're asking, but you're going to essentially say you want to look at the cumulative, right? So when you say cumulative, let me explain what this means. This is, of course, what's the probability you get 0 or less customers, which is essentially 0 customers. So the answer is same. But here, you're saying what's the probability you get 1 or 0 customers, right? So you add these two and you get 40.60%. When you want 2, 1, and 0 cumulative, then you add it again. And so let's look at the cumulative values. And as you can see, you get to about this less than 9. Most of it is covered by less than 9. Now, let's take the same question. Whether we have 2 customers coming per minute or 0.5 minutes per customer, it's the same data. It's just the units are changing, right? You have 2 customers a unit, but you can have 0.5 customers. And let's look at an exponential distribution. Remember now, with exponential, the question you're asking is not about the customer. You're focusing on the time for the next customer. So you're saying, hey, what's the probability I'm going to get my next customer in the next 1 minute? And your lambda is your average. Again, you're going to use F4. And here you're always going to put cumulative is true because this is a continuous distribution. Okay. And so here you have a 39% chance that you have the next customer coming in the first minute. And you could copy this down. So within the first minute, the probability of getting customers 39%. The probability of not getting a customer in the first minute is 1 minus this. So it's 60.5%. So probability of getting a customer in 1 minute or less, right? Probability is 39.5. More than that is 60. And then you can kind of, as you're going through, you can see the probabilities on this exponential distribution. So I hope both understood the difference between Poisson and exponential with this example. The next continuous distribution which we are going to look at is uniform distribution. Uniform distribution is a rectangle, and here we are assuming that events are equally likely to occur between the minimum and maximum values. Outside the minimum and maximum values, the probability of getting that event is 0. But inside this, it is the same probability. Now, there are very few real life processes that have this form of uncertainty. Example could be the position of an air molecule in a room, which might be important if you want to look at how things spread in a room. COVID-19, how does it spread? Now we might want to look at this uniform distribution here. The point on a car tire where the next puncture will occur. Now, if you're using this car and it's equally getting worn out on all directions, this might be something to look at. It's also called no knowledge distribution because essentially what we're saying is, hey, we know the minimum and maximum, and we really don't know anything about the distribution in between. So we have no information about this phenomena except minimum and maximum value. And in reality, it is readily possible to establish more knowledge of a situation than just the minimum and maximum value. The next continuous distribution is called triangular distribution. And here, instead of having 2 possible values, you end up with 3. You're going to have minimum, most likely, and maximum values, nothing else. So here, we use this a lot in project management. Let's take a project and break it up into small tasks. As a project manager, you might know that task A normally takes 4 days. But your best estimate is 2 days. Worst case, it's going to take 8 days. And we often have scenarios like this when we work on a project. This would come under triangular distribution. It is very much like uniform distribution, except that you have 1 extra piece of data. Now, the final distribution which we're going to look at, and the most important distribution, is normal distribution. Here we assume most observations cluster around the central peak. Probabilities for values further away from the mean taper off equally in both directions, and that's why we say normal distribution is symmetric. Let's take an example, and the example could be height of people, blood pressure, measurement error, IQ score. It is also called a bell curve. because it appears in the shape of a bell. It fits many natural phenomena, and it's also called a Gaussian distribution. Now let's look at this whole aspect of it being symmetric. Here is the center, right? This is the mean, and you see that as you move away from the center, this curve is tapering off in the same magnitude, so it's equally on both directions. So the parameters you use in normal distributions is going to be mean and standard deviation. So remember, when we did measures of central tendency and measures of dispersion, mean is the middle value of all the data, and standard deviation is the average distance from the mean. It's important that you remember these definitions. So here is an example of normal distribution having the same mean, but the same standard deviation, but different means. So the blue distribution has mean at 100, and the red one is at 150, but the standard deviation is 15. Here is another example where we have the same mean. The blue and red have average at 100, but standard deviation for the red is 30, and you can see that 30 is the spread is a lot more broader and it's less tall. So the blue distribution is taller than the red distribution, and the blue distribution is narrower than the red distribution. So the properties of normal distribution, they're symmetric, which means you cannot have skewed distribution. Skew meaning it's not at the center. So you're assuming that mean, median, and mode are equal here. So you cannot have a distribution where median may be slightly different from the mean. Half of the population is less than the mean, and the other half is greater than the mean. And then we have the advantage of normal distribution is we have something called the empirical rule. It allows you to determine the proportion of values that fall within certain distances from the mean. So let's talk about the empirical rule. One standard deviation away from the mean contains 68.26% of the data. Two standard deviations on both sides contain 95.44% of the data, and three standard deviations contain 99.73%. So let's take a look at this here. So you can see here normal distribution, one standard deviation, it's 34. Because it's symmetric, you can split 68.26 divided by 2. It's 34.13% to the left, 34.13% to the right, right? And then you're going to add another 27.28% here. So you can see as it's split into 13.59. And so here you can look at 27.72, 47.27% here in two standard deviations on both sides, and then of course it's 99%, so this is 99%. So only 0.27% is outside three standard deviations here. So 0.27 is about 27 out of 100, right? And that's beyond three standard deviations. So let's take an example. If we had monthly average sales about 3,000 and standard deviation of 100, we know that 68.26% of the time our sales is going to be between 29,000 and 3,100. 95.44% of the time it would be between 3,200 and 2,800, and then 99.73% of the time it's going to be between 3,300 and 2,700. So for you to get something over 3,300 or less than 2,700 sales, that would be about 20.27% of the time. And I apologize, I did say 0.27 was 27 out of 100. It is actually 27 out of 1,000, not out of 100. So normal distributions, we're going to look at standard normal distribution. And standard normal distribution essentially assumes mean is 0 and standard deviation is 1. This is also called a Z distribution. So if you have a distribution where you have mean of 0 and standard deviation of 1. This is called a Z distribution. Now the value on the standard normal distribution is known as a standard score or a Z-score. So Z-score is the number of standard deviations of an observation that is above or below a mean. So a Z-score of 1.8 says that the observation is 1.8 standard deviations more than the mean, and a Z-score of negative 1.8 says that the observation is 1.8 standard deviations below the mean. Now this is useful to make comparisons. Let's take height and weight. Height of let's say a basketball player is 0.3 feet higher and 50 pounds heavier than the average basketball player. Now this is 0.3 feet. If you convert this into inches, the numbers change, and it can't really compare feet and pounds, can you? It's like chalk and cheese. So, but if you say this 0.3 feet higher is 1 standard deviation away, so the Z-score is 1, and the weight is 3, which means 50 pounds is 3 standard deviations away from an average weight, you can kind of say the basketball player is 1 standard deviation more in height and 3 standard deviations more in weight. And you can compare them because now the units are in standard deviations. Furthermore, whether you change feet to height, pounds to kgs, this 1 and 3 will not change because this is number of standard deviations. So let's continue on how we calculate a Z-score. Z-score is the value you're looking at minus the mean divided by standard deviation. Go ahead and memorize this. Of course, I'll give you the formula, but this needs to be in your mind. So let's try to understand what a Z-score is. Z-score is number of standard deviations from the mean. So value minus mean is distance from the mean. And when you divide it by the standard deviations, this gives you number of standard deviations from the mean. Let's take an example. Let's say this is 6 feet and this is mean is 5 feet. That's 1 feet away. And if standard deviation is 0.5 feet, that'll be 2 standard deviations away from the mean. So let's take the example. Apples weigh 110 grams. Average weight is 100 grams. Standard deviation is 10 grams. So this apple is 10 grams heavier than average. But if you look at standard deviation, that will give you 1 standard deviation, right? Z-score of 1. Oranges weigh, let's say the orange, you're taking an orange. You go to the grocery store, you take an apple, that's 110 grams. You take an orange, that's 120 grams. And you say, hey, my orange is heavier than the apple, but you really can't compare apples to oranges, right? However, if you know the average weight of oranges is 140 grams and standard deviation is 2 grams, you will then understand while the orange is heavier than apples in grams, you take the Z-score, and apple is 1 Z-score more than its average, whereas the orange is 1 Z-score less, 1 standard deviation less than the average. You're getting a better apple, a bigger apple than a normal apple, whereas as an orange, you're actually getting a smaller orange. You see the difference? So let's talk about Excel and normal distributions. If you have a value and you want the probability of getting less than that value, you're going to use norm.dist. I'm going to open up Excel and show you how to do this. If you have a Z-score, and you want the probability of getting less than that Z-score, use norm.s.dist. If you have a probability and you want to use the value, use norm.inv. If you have a probability and you want to find the Z-score, use norm.s.inv. All right, so let's stop here, open up Excel, and we'll talk about how we can calculate the probabilities using normal distribution. Let's take an example of normal distribution. Let us decide that we are in a distribution where, let's look at salaries, and let's say the average salary is about 5,000, right? And this is your average. And the standard deviation is, let's say, $200, right? So this is essentially what you're dealing with. And now somebody comes to you and says, tell me what's the probability that somebody can get 5,400 or less. So essentially they are asking you for this area here, this area, saying what is this out of this entire bell curve, and I know this is not like a bell, but assume this is like a bell, what's the probability you are going to get 5,400 or less? Now, if you had Excel with you, you're going to use norm.inv, right? And sorry, norm.dist, and you essentially are going to put in, you have your value is 5,400, your mean is 5,000, and your standard deviation is 200, and in cumulative you are going to put true. Anytime you're using continuous distributions, you're always going to use true. So you can see 97.72. The blue area, shaded area, is 97.72%. So the probability you're going to get something which is right here. So this is 97.72. So here is going to be 1 minus, or 100% minus 97.72, which is 2.28%, right? So you have here 1 minus this value, which is 2.28%. You could ask another question. You could say, well, what's the probability that it's going to be less than, and let's take 400 less, that's 4,600. So if we wanted to do again, we're going to use norm.dist. You can plug in 4,600. This is 5,000, and this is 200, and cumulative is true, right? And you'll notice that your answer comes out to be 2.28. And so, you know, this value here is the same as this value, as you can see, right? And the reason is because it's symmetric. This is 400 less, this is 400 more, and because normal distribution is symmetric, then these values will be the same. Similarly, the probability you're going to get more than $4,600 in this company is 1 minus this value, 2.28%, which is 97.72%. So I hope you understand the whole idea behind symmetric in normal distribution. Now let's talk about if you were, let's take the same example. I'm going to redraw it again. And let's look at the probability. Let's take this example. And instead of if you're not given, the number, but let's say someone said, hey, this area here is 10%. What is this value here, right? You're given the probability, but you're asked to calculate the value. Now, if this is given as 10%, you need to calculate this area here as 90%, right? Because in Excel always takes the area to the left. So you're going to use norm.inv, and it's asking you for the probability. Do not put 10%, put 90%, right? 0.9. The mean is 5,000, and standard deviation is 200, and it will give you the salary you're going to get, 5,256.31. That corresponds to 90% of the values, and only 10% of the people get more than $5,256.31. Okay. So everybody comfortable? Hopefully everybody's comfortable with this. You should be able to, with normal distribution, if I give you a value, you should be able to find the probability. If I give you the probability, you should be able to find the value. All right. Let's answer one more question. Let us say that you were asked to find the probability that you have these two lines. Same thing, 5,000, standard deviation is 200. But here you have, let's assume this is 5,500 and this is 4,000, let's say 4,800, right? And you're saying, hey, give me the probability between these two values. And for that, what you would do is you would use norm dist, right? And you would take 5,500, the mean and standard deviation are already given. Cumulative is true. So you find the probability. That's about 99.37% of the data is less than 5,500. And then you're going to do the same thing for 4,800. And mean is 5,000. Standard deviation is 200. And this is true. And so you have 15%. And if you subtract the two, that gives you the area between the two lines. Okay? So I hope all of you are comfortable in finding probabilities, which is greater than some value, less than some value, and then between two values. All right? You also should be, if given a probability, should be able to calculate that value. Okay? Remember also that if I give you the probability, which is greater than some value, you will actually calculate the probability it's less than and put that in the norm.inv formula. Now, we did discuss two other formulas which are also used. One is norm.s.dist. In this case, you're just, if you have the z-score already, you can plug in the z-score. Similarly, norm.s.inv, if you plug in the probability, it will give you the z-score. Okay? And with this, we finish what we need for normal distribution. Some important things to remember about normal distributions before you go on to the next lecture. Important to note, mean splits the distribution exactly into half, 50% to the left, 50% to the right. Normal distribution is symmetric, so the same z-score gives you the same probability. Total area under the curve is 100%. You need to use that when you want to calculate probabilities which are greater than a value. If you are asked to input a probability, it is always the probability of the left side or less than a value, not greater than the value. Excel also will always give you the probability of less than a value, not greater than. And so you have to use 1 minus that value to calculate the value of it being greater than. Remember, z-score of 0 is exactly the mean. When z-score is 0, your value is the mean. And therefore, the probability of getting a z-score less than 0 or more than 0 is exactly 50% because the mean splits the data into two equal halves. I hope this helps you. We will move on to the more important aspects of descriptive statistics in the next lecture.